Boldly going where no science show has gone before. The Naked Scientists.
On The Naked Scientists this week, pain-free vaccinations, a new way to take CO2 out of the atmosphere, and the spores that travel on smoke rings, plus a new microbicidal gel that helps to protect women against HIV infection. Hello, I'm Ben Valsler, and with me this week for The Naked Scientists is Dave Ansell, and here's Chris Smith.
Hello, and greetings from sunny Exeter. We're taking on your science questions this week, so stick around to find out how ants can count, if rubber soles can keep you safe from static shocks, if hair can clean itself, and why shaving foam can keep mirrors frost-free. We'll be answering all of those, and if you've got a question you'd like us to solve for you, the details of how to get in touch are coming up. Dave.
Thanks, Chris. Plus, we'll be hearing from Mira about the technology of yesterday, how people are keeping retro computers going and even doing things that they were never designed for. And also this week, I've got a really sweet kitchen science for you. We're putting popping candy under the microscope to find out how it makes its distinctive popping sounds.
If you would like to get in touch with us through Twitter, it's at Naked Scientists, and our email address is chris@thenakedscientists.com.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientist with me, Ben Valsler, with Chris Smith and with Dave Ansell. And as usual, we'll kick off with a look at this week's science news. Moss spores seem to get an extra lift from the same process that generates smoke rings and mushroom clouds, according to new research published in the journal Science this week. Dwight Whitaker at Pomona College in California and Joan Edwards at Williams College, Massachusetts, realised that the spores of sphagnum moss couldn't possibly reach as high as they do by ballistic propulsion alone, so they set out to try and find the moss's trick. Sphagnum moss is thought to store more carbon than any other plant genus, and it covers around 1% of the Earth's surface, so it's a very important plant. In order to distribute its spores, it fires them upwards into a turbulent patch of air, where they're picked up and transported on eddies and breezes. To take advantage of the breeze, the spores have to be very light, and they have a terminal velocity of just 5 millimetres per second. And that low terminal velocity creates a problem when getting through a layer of still air directly above the moss, where the spores will rapidly decelerate. The spores develop in the top half of a 2 mil spherical capsule, the bottom half of which is actually hollow, it's just full of air, and each capsule contains 20,000 to 250,000 spores. But when the conditions are right, these capsules dehydrate and they become cylindrical instead of spherical. In this process, they vastly increase the air pressure in the hollow bit at the bottom. Eventually, the capsule fails and the internal pressure fires both the spore and a little puff of air upwards. And this puff of air creates a vortex. It's a sort of self-sustaining ring of rising air, very much like a smoke ring or a mushroom cloud, which is strong enough to carry the spore far further upwards than it would otherwise go, and up high enough into this turbulent air to be carried away. And high-speed imaging confirmed their hypothesis. This is really nice. Now, we know of a few species that do take advantage of vortices like this. Bees certainly do when they're flying, jellyfish underwater, but this is the very first example of vortex use in plants. Very nice.
It's really beautiful. Now, carbon capture has often been suggested as a way to reduce carbon emissions. So far, it's normally just meant collecting carbon dioxide and hiding it somewhere down a mine or down in an oil well. But the ideal solution would be some way of converting the carbon dioxide back to carbon, releasing the oxygen. The natural way of doing this would, of course, be to harvest sunlight with plants. The biomass which is produced can be sequestered. Eventually that goes on to produce oil or coal, and so forth. But the highest efficiency plants only convert a few percent of the sun's energy into biomass, and if you want to use it as a fuel, the best conversion efficiency is less than 0.5%. Now, a more radical approach to this problem has been to use solar electricity to electrolyse or split the carbon dioxide straight into carbon and oxygen. Whilst in comparison to photosynthesis this is good, it still wastes a large amount of solar energy, as most solar cells can't use the huge amount of infrared, about half the energy, which is basically just thermal energy in sunlight. Now, Stuart Licht, which is a wonderful word, it means light in German, and colleagues from Washington DC have come up with a way of increasing this efficiency. They're electrolysing carbon dioxide dissolved in lithium carbonate, so still using electricity. They've discovered that if you heat the system up to 850 or 950 degrees centigrade, you need 40% 50% less electricity to split the carbon dioxide. It's an endothermic reaction. It needs energy, and it's taking some of that energy directly from the heat. The really neat thing about this is you can use the infrared part of the solar spectrum to heat up the electrolysis cell while still using a solar cell at maximum efficiency, in fact slightly better than normal, as there's less overheating problems, to generate the electricity to split the carbon dioxide. Now, using the most efficient solar cells available, they think they can use between 30 and 55% of the sun's energy to either produce carbon directly or at a slightly higher temperature carbon monoxide. So it could be used either to sequester carbon, or the carbon monoxide could be used as a feedstock to produce hydrocarbon fuels, or in fact straight hydrogen.
Excellent. Chris?
So, Dave, if you make the carbon this way, apart from turning it into fuels, would the idea be then to put it somewhere? You could put that carbon as a solid blob of carbon back down a coal mine so that it would not then be released again back into the atmosphere?
Yeah, you could basically just bury it, and it's a much more efficient way of burying it as a solid than as a gas, because it's obviously much more condensed and involves carrying around less high-pressure gases.
Much easier to deal with.
And I suppose one benefit is you could actually use it as a fuel if you get caught short later anyway, couldn't you?
Yeah, you're essentially just making coal.
Indeed. Well, I want to have a chat this week about a story that's made a few headlines around the world. It's the idea that scientists might, by using a vaccine patch, enable us to actually dispense, excuse the pun, with needles and syringes. So this is the work of Sean Sullivan, who's based at Emory University, and what he and his colleagues have done and published in Nature Medicine this week is to turn a polymer material, it's called polyvinyl pyrrolidone, into a patch matrix. So what you can do is you make a little sticking plaster, effectively, which has all of these tiny needle-thin projections on the surface. They are tens of microns across, so very, very tiny, a thousandth of a millimetre or so across, and about 3/4 of a millimetre high. And when you apply them to the skin, they penetrate roughly about 1/5 of a millimetre into the epidermis. And the nature of the polymer means that within about 15 minutes, 90% of this polymer will have just dissolved into the skin. And what they've then discovered you can do is to embed within the matrix of that polymer dried antigen. So you can take, say, the protein, which is the coat of a flu virus, dry it down, this is a process called lyophilization, embed it within the polymer, and then when the polymer dissolves, of course, it leaves behind in the skin the antigen of the flu virus. And we know that skin is very well endowed with classes of cells called professional antigen-presenting cells, or dendritic cells. These are very good at presenting to the immune system things that they find, probably because the skin is always being exposed to various antigens. So it's very richly endowed with these cells in order to keep the immune system informed as to the kind of things we're coming into contact with. And this means that vaccines put just into the skin, rather than deep into the muscle, which a syringe and needle would do, are actually very good at driving an immune response. In their experiments, what they show is that mice can be protected against lethal doses of the flu by using this technique every bit as well as they were by using a needle and syringe, and even better if you come back a period of time later, which is probably more representative of a natural infection because most people are not immediately exposed to a virus after they've been immunised against it. What they find is that the mice they tested have a very good recall memory of the immune response. In other words, they mount a response very vigorously and very quickly. And this could make a very big difference, this kind of technique, for people who are needle phobic, obviously, but also in places like the third world, because it's very easy for us in the first world to say, well, you just give someone a vaccine, but syringes and needles are like gold dust, and because of that, when you use them overseas, there's a big temptation to reuse them, and this means they could also spread diseases. A patch like this doesn't carry that risk, and the other major benefit is that the vaccine is stable. It doesn't have to be kept cold and refrigerated, so you could just mail it out or carry it across continents with no need for refrigeration, and it will still work.
That sounds excellent. That's really what we need. But how does this compare to existing patches? Because we have nicotine patches, of course. I know there are pain-killing patches as well. What's the difference? What are they doing?
Well, those patches are relying on the fact that the drugs they're administering are very lipophilic. In other words, they dissolve in fats and oils, which means they move into the skin effectively under their own steam because skin's quite fatty, and then they get into the body. This approach is actually manufacturing a matrix of tiny needles that are so small that you don't actually feel them going into your skin, but they're puncturing the outer hardened stratum corneum, as it's known, of the skin, and carrying the antigen in with them, and then dissolving, so it leaves the antigen behind and the polymer's harmless.
Brilliant. Now, completely different subject. A new way of creating solid batteries could store more energy and make them last a lot longer. Now, lithium-ion batteries are now pretty much the standard high-performance rechargeable battery. They have a relatively high capacity and are becoming more affordable, and you find them in most laptop and phone batteries, and they've recently been used in things like the Tesla Roadster sports car. However, there are still major issues. The cathodes slowly change shape and degrade over time. This causes an electric car battery to sometimes only last 2 to 3 years, which is a real problem with a car with such a short lifespan. This is related to the batteries using a liquid electrolyte which carries ions between the electrodes, which also requires lots of infrastructure to hold everything apart, avoid short circuits and keep the electrolyte in. Now, one solution to this problem is to use solid electrolyte, which sounds quite surprising, but you can get solids which will allow ions to move within them while still remaining a solid. Unfortunately, these normally have to be made using vacuum deposition techniques like how you'd make a computer chip, which are very, very expensive, and you could never scale them up to a car battery, for example. However, a company called Planar Energy has developed a process for making these solid-state batteries using printing techniques, which are far cheaper than deposition. They've also apparently increased the conductivity of their solid electrolyte to be comparable with the conventional electrolytes, and they've made high-quality electrodes using a chemical self-assembly process, where reactions between the inks and the surface can produce complex structures with much better properties. Apparently these batteries have a capacity similar to the best high-performance conventional batteries, but should survive much longer, have about 3 times the capacity, lose energy more slowly so they don't self-discharge, and be safer than conventional lithium-ion batteries, which do have a horrible tendency to occasionally catch fire, which has caused great embarrassment to various big companies. Even if they don't manage the half the current price per kilowatt hour, which they're promising, they do sound like a very interesting technology for many applications.
Very interesting stuff. Aren't solid batteries at a slight disadvantage in because the ions have to move through something solid? It means that they take longer to charge, and actually changing the amount of current you're pulling out of one takes longer than it would do with a liquid battery.
Well, that's part of the breakthrough here, is because they've increased the conductivity of the solid electrolyte up to similar to a liquid one. That shouldn't be a major problem.
Excellent. Chris?
Yes, well, hopefully that will save me the ignominy of having my shaver go flat when I'm on holiday, which seems to keep happening if I can find better batteries for it. Well, also in the news this week, a vaginal gel, which contains the anti-AIDS drug called tenofovir, has been found to reduce transmission rates of HIV amongst women by up to 50%. And to explain a bit more about the study, which was carried out in South Africa, Slim Abdul Karim is from the University of KwaZulu-Natal, is with us now to tell us what he did. Hello, Slim. Thank you for joining us. Kick off, if you would, by first of all setting the scene for us. How big a problem worldwide is HIV? What's the scale of the problem?
Globally, we have a good idea of what's going on with the HIV epidemic. We know in 2009 that there are 33.4 million people living with HIV, and that during 2008 there were 2.7 million new infections and about 2 million deaths. So globally, the epidemic continues to grow, although it's growing more slowly now than it was some 5 years ago.
And just totting those numbers up in my head, that would mean something in the region of 7,000 people a day must be dying of HIV and 7,000 new infections every day. So we need to sort this out. Vaccines are only at best, the trial in Thailand suggests 30% effective. So you've been taking a slightly different approach, these gels. How do they work?
There have been several gels that have been made, and foams and sponges as well. And they've been impregnated with different kinds of chemicals and called microbicides. And the underlying hypothesis is that these chemicals, when put into the genital tract, to the vagina, would prevent HIV from causing infection. Well, up to now, in the past 15 years or so, there have been 11 trials of 6 candidates, none of which have been shown to work. So it's been a pretty difficult time in the field to find something that could prevent HIV infection. So we took a different approach. We decided to go with an antiretroviral drug, which is very widely used for treating AIDS. And this drug is called tenofovir. It is a standard part of many cocktails of 3 drugs that are used to treat AIDS. So we put this drug into a gel formulation, and we put it into single-use applicators, and we did a study of 889 women in South Africa where they were asked to use this gel within 12 hours before sex and within 12 hours after sex. And what we found was that in the half of the women that used the tenofovir gel, that there was 38 HIV infections compared to 60 HIV infections in those women who were using an identical placebo gel. So that translates to a 39% protective effect of this gel.
And over what period of time were you studying? How long did you look at?
The first woman was enrolled in May of 2007, and we completed the study in December of last year. So 2.5 years in total.
So if you extrapolated this to making this available to every exposed individual, let's just take Africa as an example, how many cases of HIV do you think you could prevent per year with this strategy?
So we've done some mathematical modeling, creating a hypothetical scenario as if we were implementing this in South Africa, where we have very good data. And we emulated the kinds of adherence we get within the study. So within the study, for those women who used the gel most consistently, they had 54% protection. And those women who use it least consistently, less than 50% of their sex acts, we saw 28% protection. So what we did is we modeled that. We said, okay, what if 40% of the women used it in a consistent way as we observed in our study, and 40% used it in an inconsistent way as we observed in our study? And if we did so, then over the next 20 years, we estimate we could prevent 1.3 million new HIV infections and avert just over 800,000 deaths just in South Africa alone.
And at what cost would that come at? How much would it cost to implement that?
Now, that's a bit more difficult to calculate. We know the actual cost of the gel is negligible. For the study where we only made a small quantity, so we didn't benefit from scale, the actual gel costs about a cent or two in U.S. cents. So the cost is not in the gel, but it's in the applicator and the wrapping and the packaging and so on, so that for the trial, each applicator cost us 32 U.S. cents. If it's produced to scale, we would estimate that it would go substantially less. And we've worked out that even at the current price of 32 U.S. cents, it is still cost-effective to implement, because the cost of treating somebody who develops HIV infection is so high that even at this cost, to use the gel is more cost-effective than to allow women to get infected.
Well, that brings me on to my last point, which is that the way we treat HIV is with triple therapy. We give people a combination of drugs so that the risk of the virus becoming resistant is reduced. You're using a single agent in this gel. Is there not a risk that we could end up eroding the ability of this agent to prevent HIV because people are being exposed to this as monotherapy?
Yes, it is a hypothetical concern, and certainly before the results of our study has been looked at in many different ways. These are the first data that come out now, where we can look at whether any of the 38 women who became infected while using tenofovir, whether they developed resistance, and the answer was no. We found no evidence of tenofovir resistance.
Indeed. Slim, thank you very much. That's Slim Abdul Karim, who is from the University of KwaZulu-Natal in Durban, South Africa, and he was reporting there the study that he's just published in the journal Science, looking at the use of a vaginal gel which contains the agent tenofovir, which seems to be able to reduce by a significant margin the rate of HIV transmission. We'll put details of that study and all of the other news stories that we've covered in the news this week on our website. You can find that at nakedscientist.com/news.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, Dave Ansell and me, Ben Valsler. We're answering your science questions this week, and also on the way we'll be hearing from Mira, who's been exploring vintage computers. And later on, Dave is going to have a live kitchen science in the studio. But Dave, you want to ask everyone a question about this one?
Yeah, basically the kitchen science is trying to answer the question, why does popping candy, you know that stuff, you may have had it when you were a kid. Well, I've got some in a packet over here. Here you are, Ben.
Right. Popping candy. This one's strawberry flavour. It's made of sugar, lactose, glucose. It doesn't sound very healthy, but yes, I know the stuff. It pops and fizzes in your mouth.
That's right. So basically the kitchen science is trying to answer the question, why does it go pop? So Ben looks like he's about to try some.
Oh, I think I might save it till later. I'll spoil my diet with this.
That's certainly true. So if anyone's got any ideas why it goes pop, email us at Chris the Naked Scientists.
Or you can send us a message through Twitter to @NakedScientists. Now, we have had a comment that Sarah Caster-Perry was really impressed with. Last week, Sarah mentioned that she doesn't particularly like wearing high-heeled shoes, and Clara Weinert in Rochester in New York in the US said, yeah, a woman on air who says she can't wear high heels because of quite how uncomfortable they are. Thank you, Sarah. Well, I'm sure Sarah is very chuffed about that. Now, it is a Q&A show this week, so we're answering your questions, and on the line we have Rafaela. Hello, Rafaela.
Hello. My question today is why, when you're in water, do you get wrinkles?
That's an old classic one. Always a problem with going swimming as well. Chris, I think this is probably one for you.
Thank you, Ben. Hello, Rafaela. Welcome to The Naked Scientist. The reason that you get wrinkly fingers in the bath is because the skin on your fingers and hands and toes is quite thick, and it's there to protect you. You have a slight thickening of the skin because we tend to rub our fingers against things more often than we rub other bits of our body with things, and the skin becomes thicker there to compensate. And the top layers of that thickened skin are flat, dried out, dead cells. In fact, they're falling off of you all the time. If you could tot up the number of cells that you're losing, it's about 40,000 skin cells a minute fall off you. If you added them all up, 1.5 stone in dead skin over a lifetime. Now, that dead skin on your fingers, which is still attached, despite being a flattened, thick layer, is nonetheless, it's slightly penetrable by water. And water can get into that layer, and it makes the thin, flattened cells swell up a bit. And in the same way that if you make railway lines very, very warm, they can buckle and bend, which is why you have to leave a gap between them. The skin cells do the same thing. They swell up, they press into each other, and as a result they push each other out of the way, and they get thrown up into all these ridges and folds because the cells are bigger, because they've got water in them. And then after you get out of the bath or the sea or the swimming pool and you dry out again, that extra moisture that's gone into the cells comes back out, the cells flatten out again, and they go back to their normal shape. And that's why you go all wrinkly in the bath.
Thank you.
Well, thank you for your question, Rafaela. Thank you very much. Dave, we have one for you here. Interesting one, and possibly inadvisable, but it's from Clive Pounds. He says that recently a friend of his was going to use a metal knife to free some stuck toast from the toaster, and he's always been told this is a huge no-no, and by and large I think sticking metal things in electrical appliances is indeed a large no-no. But apparently his friend said it would all be fine because he had rubber-soled shoes on. So is it true that rubber-soled shoes will protect you from an electric shock?
I think the simple answer is it is possible they would protect you from an electric shock, but it's not something I would ever recommend because it's only possible. If you've got a big thick rubber sole, then you're quite insulated from the ground. And if there's no path for electricity to flow through you, you won't get a big current go through you, so you'll be fine. It's essentially a similar reason to why birds can sit on electricity cable. They might be sitting on a very high voltage, but there's no path for electricity to get down to earth through them, so they're absolutely fine, there's no current flowing. So as long as you're just standing on your shoes, you're not touching anything else, your feet aren't wet, so they're not creating a short path around the rubber soles to the ground, and you're not accidentally touching anything metallic, so if you were touching the outside of the toaster, which might be earthed, then you might get a horrible current going through the knife up your arm, then down the other arm, then you might be okay. But there's so many things you could possibly go wrong. Unplug the toaster first.
I think that sounds like sound advice. And by and large, don't stick metal things in electrical appliances.
When you look at the glowing filament in the toaster, Dave, are each of those wires in the toaster actually running at 240 volts? Or does the toaster step the voltage down? Are they all in series, so there's big voltage drops, the actual potential on each of them is quite low? How's it work?
It's basically just a very long piece of fairly high resistance wire. I've taken a toaster apart recently, so I know this. It starts at one end, it kind of zigzags up one side, then the current flows down and then zigzags up along the other side. and then it's attached to the neutral wire. So one end of it is going to be at 240 volts, the other end is going to be at about earth. So if you stick something metal anywhere near the 240 volts, even 100 volts, you're going to get a big shock.
But if you were lucky and you got it to the neutral end, the potential there's a bit lower. So if you were making a toaster, hopefully you design it with the most inaccessible bit of the high resistance filament furthest away from where the knife's going to go.
Looking at how the toaster worked, one of the holes is going to be more dangerous than the other one, but they didn't seem to have made any particular attempt to make one side more difficult to get at than the other.
They assume people have got some common sense after all.
Exactly. I guess if the general rule and the general understanding is don't stick metal cutlery in your toaster, then the other safety features are probably obsolete. Chris, we've had another question here, this one from William Baker, and he is very kindly said that he really enjoys the shows, which is very nice, and he listens to the podcasts while working a night shift at a hotel in Fairbanks. Sounds very glamorous for us here in Cambridge. But he wants to know if there are any foods that will affect the flavour of breast milk.
Well, we have looked at this actually as a news item on The Naked Scientist. A couple of years ago, there was a paper we reported. I actually gave it the exciting title. Hang on, I'll just read it to you. I said, "Fulsome Flavours on Offer at the Breastaurant." It was actually a piece of work done by a lady called Helene Hausner, who is from the University of Copenhagen. It was a paper published in the Journal of Physiology and Behaviour in 2008. What she did was to investigate this very phenomenon, because women, including my wife, who have had babies, often report that certain things they eat will affect whether or not the baby is very enthusiastic to breastfeed or not. And so to get to the bottom of this sort of transmission between food and breast milk flavourants, this group recruited 18 women who were breastfeeding at the time, and they got them to give some milk samples before and then milk samples after. They gave them some capsules containing various flavourants. The flavourants they tested were menthol, we all know what that is, also a chemical called D-carvone, and carvone is the stuff that makes caraway seeds have that very aromatic flavour to them. They also tested a chemical called 3-methyl acetate, which is a banana smell, banana flavour, and transanethol, which is a sort of licoricey taste. It's the thing that makes star anise and licorice and ouzo taste the way it does. And by feeding the women these things and then taking breast milk samples from them for certain amounts of time afterwards, up to 8 to 10 hours, and then measuring the volatiles, the smells above the breast milk, they could work out roughly how much of these flavourants were getting into the breast milk. And it wasn't trivial. In fact, they found that different times elapsed for different flavours. The menthol took about 4 to 6 hours to peak. The carvone and the transanethol took about 2 hours to reach peak levels. But the banana flavour, the 3-methyl acetate, didn't come through at all. And the interesting thing was that there was an 80% difference in the levels of these different smells and tastes between different groups of the women. So if you look at one woman and compare another woman for the same flavour, you might detect 80% more or less of that flavour in her breast milk compared with the other woman. And if you do the test more than once on the same woman, you might find more than 50% variation in the levels of these different flavourants in their breast milk. And what this shows you, therefore, is that it makes a very big difference from one person to the next. It makes a very big difference even in the same person. But the bottom line is that things that you eat definitely can end up going into your breast milk. And it's not just small molecules and flavourants, it's also whole proteins. And researchers back in the 70s have done studies by radioactively labelling proteins and amino acids and then sending them through in the diet and tracing them out into breast milk, showing that they do then end up going out and going into the baby. So people who say their babies do develop taste for things based on what mum's been eating are absolutely right.
How well developed is a baby's sense of taste, then? Do you think the babies can actually taste this?
It's almost certain that they can. If you think about it, the baby, when it comes out, is very underdeveloped and tends to prioritise the development of the systems that enable it to succeed when it's little. So it tends to develop first the things that will be most essential to survival. That includes knowing when something's good for you and bad for you and how to alert mum with a cry. And babies, if you want to encourage them to eat something, they've got to like what they're eating. It's a sort of reinforcing thing, isn't it? The brain has to say, I like this, I want to do it more, which makes sure the baby feeds regularly. So it's almost certain that babies do get hooked on these flavours.
Well, thank you very much. We are going to go back to the phone line now. We have Beverly, who's calling in from Norwich. Beverly, thank you so much for joining us. What can we do for you?
Well, the first firstly, I'd like to say we love your programme completely.
Thank you.
My question is this. Can we justify an involvement with nuclear power in the UK when we have the greatest potential for renewables in Europe? If we think about offshore and onshore wind power, tidal power, offshore barrages, we have a fantastic potential with a very low level of risk. And if we compare that to nuclear power, we have to look at the question of cost. And without government subsidies, the cost per unit of electricity generated by nuclear power is not cost effective. We have to look at safety and say we have a terrorist risk, we have health concerns of cancers with far higher clusters around existing power stations. We have an accident risk, for instance, in Chernobyl. We have to look at disposal of spent uranium and say, with all due respect to the spokesperson last week, it is arguable that it is not safe to dispose of spent uranium, that the half-lives of spent uranium exceed the capacity of metals that we know to survive in corrosive salt water.
Some very compelling arguments there, I'd say. Thank you very much, Beverly. This is certainly one. Dave, you're a physics guru. You know a lot more about nuclear power. What are the arguments in its favour?
Basically depends how bad you think burning coal is. I mean, burning coal actually releases more radiation into the environment than nuclear power ever has, even including things like Chernobyl. Basically because there's a load of radioactive elements in coal, you burn it, they get released, you can't constrain it. Also, burning coal obviously produces lots of carbon dioxide, which is bad for all sorts of other reasons, and greenhouse effect, etc. There's also issues with acid rain, which have been largely improved. But we're getting huge amounts of our energy at the moment from fossil fuels. If you take out the nuclear power, which is a very, very dependable form of power, you know it's going to work. If you replace it with something like wind power, for a start, I think it's very, very difficult to supply the amount of energy we're using in this country using just renewable sources. There's a professor at Cambridge, David Mackay, who worked out you'd have to, in order to produce all the energy we use in this country using wind power, you'd have to completely cover the whole of the coast with order of miles of wind turbines in order to generate that amount of power. And, I mean, nuclear power does have a lot of disadvantages, but it does have the advantages that it's there, it's predictable, you can store the energy, but you're not dependent on foreign sources of energy. So if someone stops supplying you with uranium, it's very easy to store 10 years' worth of power. I mean, whilst in the long run it might not be what we want to be using, depends how dangerous you think radiation is. I mean, if you get a heavily radiated area like Chernobyl, it might not be particularly good for humans, but actually if you look at things like the amount of biodiversity there, how well the animals are doing, it's a lot better than anywhere humans are. Humans are a lot worse for the environment than radiation is. And so, I mean, there's all sorts of positives to it, there's lots of negatives to it. On balance, I think it's probably worth using, at least until we develop something better.
Beverly, I appreciate that we may not have completely turned you into a fan of nuclear, but does that help, hearing some of the positive arguments?
It's certainly interesting to see it in the round. I think your colleague was not addressing the issue of renewables as much as existing alternatives. And yes, we've got to look at how do we bridge the next 30 years and how do we use electricity, what sources are we going to use.
Well, it's certainly something that we'll have to keep an eye on. Thank you ever so much for your call. That was Beverly in Norwich. You are listening to The Naked Scientists, and this week we're taking on all of your science questions. If you would like to get in touch with us through Twitter, it's at Naked Scientists, or you can send an email to chris@thenakedscientists.com.
Keeping you abreast of the world's best science. The Naked Scientists.
This is The Naked Scientist with me, Ben Valser, with Dave Ansell and with Chris Smith.
And now it's time to join Meera Senthilingam, who's been getting a bit nostalgic and possibly claustrophobic too in this month's tech segment.
Once again, I've come down to the BBC in White City in London to meet our resident technology expert, Chris Vallance. But this time we're doing things a little bit differently because we're inside a pod inside one of the BBC cafes.
Yes, we're in the cafeteria. We hurried out of the rain and we chanced upon an experiment. We're in an experimental pod for confidential meetings. It's really just a small glass or sort of perspex room.
So this is a bit of an architectural trial, shall we say, but what have you been up to in terms of technology recently, Chris?
Well, I've been travelling back to the future. I went to Bletchley Park. Now, Bletchley Park is an interesting place to go visit if you've got an interest in technology. It's obviously the home of Britain's World War II code-breaking efforts. And if you go there now, you can see a lot of the pioneering early electronic digital computers that were used to crack German codes. Pioneering work by people like Alan Turing. It's also home of the National Museum of Computing. But over the summer, it played host to Britain's first Vintage Computer Festival. What's a Vintage Computer Festival? Well, if you're of a certain vintage yourself, like me, a child of the 70s or a child of the 80s, you may remember BBC Micros, ZX81s, VIC-20s, Commodore 64s. Perhaps you remember an Aquarius or an Acorn Electron or a Sinclair QL. All those machines and the enthusiasts who look after them and repair them were there. 2,000 people came along to look at these things. People were doing really interesting things with the old bits of kit. They were pushing the machines to their limits, getting old games, repairing machines. There was even a ZX Spectrum, which people had connected up to the internet, and you could Twitter from the Spectrum. Other kinds of things were people really just seeing how far they could push the graphics and the sound and the processing power of these machines. For example, one group was showing off a ZX81 running an image of a bouncing ball, a three-dimensional bouncing ball, and that doesn't sound very particularly impressive by today's standards. But when you consider how basic the machines are, that's quite a challenge. So people doing things like that. Some groups were actually sort of continuing to update the machines and to bring out new versions of them because they, if you like, they enjoyed the way the machines work. So there's a big group of people who are very enthusiastic for the Amiga, the Commodore Amiga. There were new versions of that machine coming out and on display at the show. Well, it wasn't just the machines that were from the 1980s. I spoke to Chris Searle, who used to present the BBC's computer show.
In the early 80s, I co-presented the BBC's first ever television series dedicated to computers, and it was the series which gave rise to the development of the BBC microcomputer, which ended up in every school in the country.
What's the importance, or maybe just what's the joy of events like this?
It's the first time this has happened, and I think it's ridiculous that it's taken this long, actually. I mean, arguably, the scientists in this country invented the computer.
Tell me why you're here.
Because I love computers. I mean, you go to see loads of other things that are really old. You go to see Spitfires and Lancasters and stuff like that, and it just makes a change to go and see something else.
Commodore 64, I guess, a 1980s machine?
Yeah, 80s. I can't quite remember where I played around with my one, but yes.
Well, I just made you crash as well, I'm very sorry. You were flying a yellow spaceship, shooting lots of things, and it's all gone wrong. Do you work in computers?
Yes. Yeah, these are the reasons why I still do what I do today. My dad brought one home, and ever since then, it hasn't really been a day gone by where I haven't played with the computer. So,
what have you enjoyed most? What's the thing here that you've liked playing on most?
The games over there, because it's brought me a bit more to like computers now.
And the games over here, they're quite simple. I mean, the one over there that you're pointing at, that's Space Invaders, which old people like me used to play. But you still quite like it?
Yeah, because it's quite a short game. If you were getting ready for bed and you just wanted to play a quick game on the computer, you could just choose Space Invaders.
So the old machines were a hit, even with those who'd never experienced them the first time round.
Now, Chris, did you have a go on any of the old machines, and how were they functioning?
Well, I mean, it was all great. I mean, I remember them from being a kid. And I think what did I have? I had an Acorn Electron. I think what's interesting is just that people are using the old machines to do new and interesting things. For people who enjoy programming and enjoy tinkering with electronics, there's something of a challenge to get an old machine to do things that it wasn't designed to do, and to having a limited amount of power and resources at your disposal. I mean, millionths of the kind of memory that you have even in phones. I mean, if you think about it, ZX81 had, a 16K memory if you bought an expansion pack. I mean, my phone's got 16 gigs on it, so I mean, that's a millionth of the capacity. And I think one of the interesting things is, for the younger generation, the games are still fun, and the machines are still fun to play around with, and they really do sound like computers. There's something about that retro beeps and bloops and the noises they make that's really endearing.
Making a machine do what it wasn't designed to do. I think Lada cars pioneered that concept with the heated rear windscreen that doubled up as a hand warmer to keep you from freezing when you were pushing. Anyway, that was Chris Vallance, and he was showing Mira Senthilingam how to make the most of your old computers, and also revealing how computers, and not just clothing, are valuable when they're vintage.
Right, Ben, we've got a question here, possibly for you. It's from Ransom, and he says, how does hair clean itself?
Now, that's a good question. I think he's probably referring to the idea that if you stop washing your hair for 6 weeks or so, then it ends up sort of auto-cleaning and you end up with clean hair despite it not being washed. I think the truth is a little bit more complicated than that, and it's not that your hair is clean, it's that your hair has the right amount of oils. Now, normally, when you wash your hair with shampoo, it's a detergent, it will strip the oils off your hair, and hair is supposed to be a bit oily, so your hair follicles produce additional oil to make up for the oil that's been washed away. You end up getting greasy hair. If you don't wash it away, there seems to be some kind of feedback mechanism that means that the follicles will produce the right amount of oil and you won't end up with greasy hair. Now, I don't know if this really bears itself out in practice, and from what I have seen and read about it, it seems to be much better for people with very short hair. And it's not that they never wash their hair, it's just that they don't use soaps or shampoos, they just wash it with water. The water takes away the dirt and the grime, but the oils stay there to help protect the hair. Dave, you've got quite a lot of hair. How easy is it for you to manage?
Well, a while ago, purely in the spirit of scientific inquiry, much to the annoyance of my then girlfriend, I decided to see what would happen if I didn't wash my hair for 3 months.
Right.
And basically what happened is my hair sort of reached an equilibrium. It was much less greasy than it would be just before you'd washed your hair normally, but still greasier than just after it. So a bit greasy, but not very greasy. So there does seem to be some kind of feedback loop. And also interesting things happened when it rained, because it appears that your natural grease from your hair is quite good at waterproofing, because the outer layer went incredibly greasy and the rain would run off whilst the hair underneath would be entirely dry. So obviously natural oils have advantages over conditioners.
That's very strange. It's like wearing a natural shower cap made only of hair. That's revolting. Quickly moving on, it's time for our kitchen science. Now, we've already asked you what it is that makes popping candy do its stuff, and now we're going to find out through the medium of experiment. So Dave has given me some of this popping candy. If I pour a bit out, you can hear it in the packet there. It looks a bit like brown sugar. It's small crystals, small rocky lumps of yellowish stuff. It smells, in this case, of strawberry. I'm just going to pop some in my mouth and see what happens, see if it does indeed pop. So here we go. Now, that's not a very nice noise, so I'm sorry for that, but I can tell you that it is popping in my mouth. I can feel all of these little crystals going pop, and that's obviously what you can hear. But Dave, what's going on?
Well, when I saw this as a kid, and ever since, until quite recently, I thought that basically it was a bicarbonate of soda and lemon juice type of reaction. So the water from your mouth was causing a reaction, allowing a reaction to happen, and that was pressure was building up somewhere and it was going pop.
A bit like the sort of fizziness of sherbet.
Yeah, that sort of idea. So with sherbet, you've got citric acid, which is dry, you've got bicarbonate of soda, which is dry. When the water from your mouth mixes the two together, the acid can then react with the bicarbonate of soda, releasing lots of carbon dioxide and lots of fizz. Then thought we ought to try and work out what it is going on with this popping candy, which makes it go pop.
But how do you eliminate that as an idea?
Well, I guess the first thing we should do, there's various things which could be causing it to go pop. One is the temperature of your mouth, I guess. The other one is the wetness of your mouth. So the first one we thought I'd eliminate is the temperature of my mouth. So I've got a cold saucer of water here, and I can put some popping candy on top of that.
So if it doesn't make any noises, then we know it's because it's too cold. So we'll put a microphone on your saucer of popping candy. Let's hear what happens. Straight away you can hear it popping, so it's obviously not to do with the temperature of your mouth. But obviously we haven't ruled out the liquid.
That's right, so I'll try and get that out of the way. It's probably going to sit there popping for a while now.
So what else can we look at?
We can look at what happens when you just physically break the little rocks. So what I've got here is a pestle and mortar. I'm going to first start off by breaking some sugar to sort of act as a control experiment.
Okay, now, I can tell you straight away that this can't be the mechanism for it popping. It can't be to do with breaking them, because I haven't had to chew this. It instantly started fizzing in my mouth without any effort on my part. So what are we going to learn from physically breaking it?
Let's find out.
Right, just going to explore the physics of popping candy by breaking it. I see you've got a pestle and mortar there, so we'll start off with some sugar, and this is just to tell us what normally happens when you break up crystals of sugary stuff?
Yeah, basically popping candy is mostly sugar, so if we listen to this, you get sort of a fairly quiet, kind of gentle crunching noise.
Yes, it's not the most pleasant sound, but it's a sort of normal, grating, crunchy, sugary sound.
Now I'll try some popping candy in there. Put it in. And I'll try crushing that.
Oh! It's much louder, much sharper. And by the looks of it, there are bits of popping candy going all over the studio now. So it's not just being crushed, they're actually exploding.
That's right, they are actually going pop just by crushing them. And you can do the same thing in your mouth by, between your teeth, actually just crushing one down. It will go pop, even if you keep your teeth absolutely dry.
So the fact that it acts very differently from sugar under pressure, there's no liquid there, this definitely rules out the idea of it being an acid-base reaction, because there's nothing to dissolve the acid there. So what is going on?
Well, I looked into this a bit more, and it turns out the way they make it is by getting sugar and a load of lactose. They melt the two of them, get it really hot, in an atmosphere of carbon dioxide. This isn't just normal carbon dioxide, it's carbon dioxide at 40 atmospheres, so very high pressure carbon dioxide. So this carbon dioxide dissolves in the sugar, then cool down the sugar, and eventually they drop the pressure. At that point, the big bubbles in it will explode, causing it to break up into little rocks. But inside each of these rocks, there's lots of little tiny bubbles, and these tiny bubbles are still at about 40 atmospheres. When you break a little lump of candy in any way, this pressure is released, so it goes pop. You can either break that physically, like we were doing with the mortar and pestle, or you can do it by adding water, which weakens the sugar to the point at which the little bubbles are strong enough to break the sugar apart, and the thing goes pop.
So they are actually full of high-pressure carbon dioxide?
Yes.
That's incredible. How does this compare to other popping foods? So we've already discussed the acid-base reaction where you get a fizz from the chemistry, but there are other foods that are known for their snap, crackle and pop type noises. Is it the same thing happening with them?
Well, these are sort of the toasted rice snacks, or breakfast cereals, I think the ones you're thinking about. These are made by getting little rice grains and then very, very quickly heating them up very, very hot. The water inside the rice boils, its pressure increases. It also sort of dissolves the starch in the rice grains and sort of forms a bit of a foam. Then the steam, the high pressure water vapour, expands very rapidly and pushes them out to create the sort of spherical cereals that we all know and love.
So it's very similar to popcorn?
Very, very similar to popcorn, yes. Harder to do, and you need different sets of conditions to make it work. But yeah, basically popcorn. Then when you put them into the milk, this very, very hard, brittle structure which is created as the starch cools down is sort of distorted, and that increases the pressure in some of these little air cavities until eventually they break and sometimes they kind of crackle or pop.
So there aren't many foods that sell themselves on the noise that they make rather than what they taste like, but that's two of them and that's how they work. We will put some details about this and sound clips, hopefully not too many sound clips of me with a mouthful of popping candy, online at thenakedscientists.com/kitchen science. Chris, a couple of weeks ago we were talking about the fact that spiders and ants are actually capable of counting, and Anne has emailed in to say, how does it work? How do they count?
Yeah, well, not just spiders, but probably many insects can do this. The example I gave was spiders counting their steps in order to know how to build their webs. But also there was a very elegant paper, it was published in Science a year or so ago by Matthias Wittlinger, who's at Ulm University in Germany. And he and his colleagues were looking at how ants navigate. And ants use the sun. They also use a compass. They have in their brain a body clock, and they're able to use this mental compass of the time of the sun moving across the sky to navigate by. But they also count their steps. And the reason that the scientists know that for sure is that they perform the very delicate task of putting ants on stilts. They cut hairs off of the back of a pig and then glued those hairs onto the ant's legs to lengthen the ant's legs. And when they did this, of course, the ant's strides became twice as long as they would normally be. And when they followed the ants around, all of the ants overshot their nest because they walked twice as far as they should have done. When they actually paradoxically cut the ants' legs off, so they had much shorter legs, they didn't walk far enough, and they were all circling around thinking, where's my nest? I should be there. And it was clear that they're actually counting the number of steps they'd taken in order to find their way around. So in their brain and their nervous system, they must have some kind of neural integrator circuit that every time they take a step, it notches up another 1, 2, 3, and so on, so they can find their way around by counting steps. So there's the evidence ants can do it. It's likely that other insects probably do the same.
So ants on stilts will overshoot their home, poor ants. Dave, we've had a question from Brett Kuiper, and he wants to know why putting a thin layer of shaving foam on a mirror will stop the mirror from steaming up.
In some senses, it doesn't actually stop it steaming up. The steam is lots of little droplets of water, which when the light hits it, it gets bent, and so you get a very kind of distorted image, which when you move away from it, it just looks like a kind of mist. What the shaving foam does is it's got lots of detergent in it. That detergent makes it much easier. It reduces the surface tension of the film of water, so it doesn't form lots of little droplets. It just forms a big flat sheet, and the big flat sheet you can see through much better. So you can see through it even though it's still the water's still condensing.
So there's literally the same amount of water there, it's just the structure of the water. So why do the droplets make it so hard to see things?
Because water has quite a high refractive index. When light hits it, it bends. And so if it hits this curved surface of a droplet, each one basically acts as a little tiny lens. So the light gets bounced off in all sorts of different directions and makes it look essentially white and breaks up the image and makes it look misty.
Fantastic. Well, very interesting. Not perhaps what you're supposed to use shaving foam for, but if it works, it works. And now we need to find out if Diana O'Carroll can achieve liftoff in our question of the week.
This week we're tooting for the stars.
Hello, Naked Scientists. My name's Matthew, and I've been enjoying your show for some time now. Recently, you featured a question about how much force a stream of wee exerts against somebody who's standing. In a related area, and being the mature, intelligent adult that I am, I was wondering, how much gas would somebody who weighs 10 stone have to expel and at what force in order to lift themselves 1 inch off the ground? Thank you very much.
Just how much gas is required to propel oneself from the ground?
My name's Dr. Mark Looney, and I'm a science communicator from Cardiff. If you weigh 10 stone, or 63.5 kilograms, then the Earth pulls on you with a gravitational force of 622 Newton, which you have to then overcome if you want to lift off for even a fraction of a second. So you have to direct a force at least this strong towards the ground, which according to Newton's second law will be equal to the mass of the gas you expel multiplied by the acceleration given to it by your bowels. That means you could give an enormous amount of gas a small acceleration or give a tiny mass of gas a huge acceleration. So how much does the average emission weigh? This is quite tricky to measure since methane is lighter than air. You actually weigh more after letting rip a right humdinger on Boxing Day due to this slight loss of buoyancy, assuming that is that you don't also follow through with non-gaseous matter, an act commonly known as sharting. Incidentally, pure methane is also completely odourless, which proves that every real fart is actually a shart in disguise. Now, having asked Jeeves what the mass of the average human trump is, given the density of methane and the pressures and temperatures found in the bowel, he returned, admittedly with his nose turned up even higher than usual, with an answer of 0.037 grams, or 0.000037 kilograms. So, to generate the upward force required to oppose gravity, your bowel muscles must give this mass an acceleration of 622 divided by 0.000037 equals 17 million meters per second, almost 2 million times the force of gravity. Assuming it's expelled in a 1 second toot, that yields a final exit velocity of 17,000 kilometers per second, which is equal to 37.6 million miles an hour, or 18% of the speed of light. Anyone capable of achieving this feat is invited to contact the UK Space Agency with a view to highly profitable long-term employment.
And you'd well and truly break the sound barrier. That's one sonic boom to remember. And on the forum, RD suggested that you could use all your waste to produce biogas, which is mostly methane, then burn the methane to power a hot air balloon to lift you off the ground. And Giza warned that, with all the gas decompressing as it exited you, it would produce an extreme cooling effect, which could freeze your bottom off. Our next question of the week.
Hello, this is Julia. I'm from Edinburgh, and I was wondering, what's that distinctive smell after it rains?
Let us know what you think by emailing chris@thenakedscientists.com or by writing on the forum, and that's at thenakedscientists.com/forum.
That was Diana O'Carroll with our question of the week. You've got lots and lots of time to consider this one. Diana will be back with the answer in September after our summer season of special pre-recorded programmes. Until then, send your answers to chris@thenakedscientists.com or write them on the forum at thenakedscientists.com/forum. But that's all we have time for this week. Next week, we've got a special show looking at the science and engineering behind the Glastonbury Festival. We'll find out what it takes to turn a farm into a city and back each year, and explore the scientific issues under discussion during the festival. If you've got any questions or comments for us, you can email us, chris@thenakedscientists.com, or tweet @nakedscientists. If you'd like to catch up with anything we've done, see our experiments, or follow up on any of the news stories we've covered, join us online at thenakedscientists.com. Many thanks to Slim Abdul Karim and Chris Valence for joining us this week, and to our production team, Sarah Castor-Perry, Tom Simpkins, Mira Senthalingam and Diana O'Carroll. The Naked Scientists was produced and presented by Chris Smith with Ben Valsler and Dave Ansell. It was produced in association with the Open University. To discover a whole range of science content, including lots of interactive features, log on to thenakedscientists.com and follow the links to the Open University.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.